Have you ever encountered a situation where you run the exact same code? Not a single character changed, not a single line moved, parameters identical, input data exactly the same. The first run takes 10 milliseconds, lightning fast. The second run takes 14 milliseconds, a bit slower, maybe just a fluke. The third run jumps to 27 milliseconds, nearly triple the time. Sometimes the difference is even more than double. You start wondering, is there something wrong with your computer? Is the CPU aging? Is there a memory issue? Or maybe the compiler or runtime environment is acting up? None of that is true. The computer isn't broken. The code is fine. It's your understanding of program performance that's fundamentally flawed. We tend to think that a program's runtime is a fixed number. Given the same input, same code, same hardware, the runtime should be exactly the same. But reality is quite the opposite. A program's runtime is never a fixed value. It's a probability distribution. In this video, we're going to dismantle a common cognitive error many programmers make. Your program has always been randomly slowing down. Let's start with the most basic misconception. Most programmers have a default mental model of performance, which is pretty simple. You hand the code to the CPU executes it, and you get a runtime. For example, take the code on screen, a for loop summing up an array. Many people think that since the number of iterations and the array length are fixed, the runtime should be constant. Where does this model go wrong? It's wrong because it treats the computer as a completely quiet, completely dedicated machine. But in reality, our programs never run in a vacuum. First, the CPU itself is not a constant speed motor. Many people assume the CPU runs at a fixed frequency, but that's not true at all. All modern CPUs have dynamic frequency scaling. It's a fundamental hardware level design that can't be avoided. In simple terms, when the CPU is idle, it automatically lowers its frequency to save power. When temperature rises, it also throttles down to prevent overheating. And when faced with a high load, it activates turbo boost to temporarily increase frequency for faster execution. For the same piece of code, the first run might happen when the CPU is in a low load state and turbo boost kicks in, making it fast. The second run might occur right after the CPU finished some background tasks, temperature is up and it throttles down. The third run might coincide with power saving mode, effectively halving the speed. This alone means that the underlying hardware speed for each program run is inherently variable. So if you try to use a single runtime as a benchmark, it's invalid from the hardware level alone. Second, the operating system never lets your program have the CPU all to itself. Do you think your program is exclusively using the CPU? Not at all. One of the core tasks of an OS is process scheduling. While your program is running, the OS can pause it at any time, switch to another task, and later resume your program. What can get inserted in between? Background browser tabs, system update services, antivirus software, disk monitoring tools, or even just switching to another window, triggering the desktop rendering process. All of these can seize CPU time slices. This switching and waiting time is entirely random and uncontrollable. Sometimes the switch is quick, so the runtime stays low. Other times the switch is slow, adding a few milliseconds of wait time and directly increasing the program's runtime. And this is just process scheduling. Hardware interrupts and soft interrupts have an even bigger impact. For instance, when the network card receives a packet or the hard drive completes a read-write, it triggers an interrupt. The CPU must immediately pause the running program and handle the interrupt. This overhead is also random and is another major reason why program runtimes fluctuate. Moreover, cache state is the most subtle performance killer. Here's a hardware fact you must remember. The CPU does not directly access main memory. The latency of memory reads, writes is tens or even hundreds of times slower than CPU cache. When the CPU needs to read or write data, it prioritizes using the various levels of high-speed caches. Modern computers generally use a 3-level cache architecture. L1 cache is the fastest with the lowest latency, dedicated to each CPU core. L2 cache is next, also core dedicated. L3 cache is shared across cores, a bit slower. Finally, RAM, the slowest of them all. The critical issue is that every time your program runs, the contents of the cache are completely different. If the data your program needs is already in L1 or L2 cache, a cache hit, the CPU retrieves it instantly and the code runs very quickly. But if the data isn't there, a cache miss, the CPU has to go all the way to main memory to fetch it. The latency of this single operation can increase the runtime by tens of times. What's more, because caches are shared across cores, other programs can overwrite cache content at any time. The cache state for each run is random and uncontrollable. Finally, the most overlooked source of systemic interference. Your program faces competition for system-wide resources. Contention for hardware, memory, bus, and other resources can directly slow down execution, and you have no control over it. Specifically, memory bandwidth is limited. If other CPU cores access memory at the same time, they compete for bandwidth, causing your program's memory access speed to plummet. In server environments, NUMA architecture can cause cross-node memory access latency to double. TLB, translation look-aside buffer, misses add extra time to query page tables. Even other programs running on neighboring CPU cores can compete for system buses and shared caches, indirectly affecting your program's performance. Beyond these 4 core reasons, there are several frequent hidden factors in daily development that make runtime fluctuations even more pronounced and that you need to watch out for during performance testing. Hardware and soft interrupts, network packets, hard drive completions, signals from external devices all force the CPU to pause your program and handle the interrupt. The overhead is random and uncontrollable. Virtual machine and runtime interference, languages like Java, Go, and Python, which run on VM or interpreters, can experience much greater performance variability than compiled languages like C or C++, due to factors like random garbage collection triggers and the initial compilation overhead of just-in-time compilation. Memory paging. When the system is low on memory, the OS may swap some data out to disk. Disk read-write speeds are tens of thousands of times slower than memory. If this happens, your program's runtime can explode. System power policy. When your computer is on a power-saving plan, the CPU frequency scaling strategy is extremely conservative. On a high-performance plan, the frequency remains stable. The performance difference between these 2 modes can reach over 50%. Simply put, you're not running your program on a quiet, dedicated machine. You're running it in a chaotic system with multitasking and resource contention. The tiny fluctuations in each stage ultimately translate into variations in your program's runtime. At this point, we can draw a conclusion. Program runtime is not a single fixed value. It is a set of probability distribution results. So the wrong way to say it is, this piece of code takes 10 milliseconds to run. The right way is, the runtime of this code is likely to fall within the range of 8 to 20 milliseconds, with extreme scenarios potentially yielding higher values. It's a range of fluctuation, not an absolute constant. Now that you understand the underlying principles, when it comes to practical application, don't just run a benchmark once, get a single number, and draw a conclusion. Instead, you should, first, warm up the program to eliminate cold start interference. Before officially measuring, let the program run several times to complete just-in-time compilation, cache loading, and other initialization steps. Once it's in a steady state, then start recording the runtime. Second, run multiple times and focus on the distribution, not single values. Run it dozens or even hundreds of times and discard extreme outliers. Don't just look at the average, pay close attention to the range of fluctuation, the variance, and the 95th or 99th percentile values. These are what users actually experience. Third, prioritize optimizing stability, not just raw speed. What online services fear most isn't being a bit slower, it's random stuttering compared to chasing the single fastest runtime. Smaller fluctuations and more stable performance are far more important for user experience. Finally, isolate the testing environment to reduce external interference. Close all unrelated background processes and system services, bind the program to specific CPU cores, and enable high-performance power mode. Minimize external factors that could skew the test results. I hope that after today, everyone will remember this core concept. Performance equals distribution. Performance is a distribution, not a single value. See you in the next video.